Subspaces of Rn. Alright, so what we have here is us taking this notion of Rn and saying, alright, if I visualize it as this blob, is this little blob inside of it a space in its own right? So here's how we can rigorize this. So we say a subset S of Rn is a subspace if the first thing happens, it contains the zero vector. The next thing that must happen is if I take any two vectors in my subset, then the sum of those vectors must be in the subset. If I take any vector in the subset, any scalar multiple will end up being in that subset. And so if you think about a vector space, that's what we've been studying here, we keep on coming back to this notion of linearity. You know, if I take a constant, multiply it by a vector, and add it to another vector, we somehow preserve this. We studied this long ago with linear transformations. A function's linear transformation if it preserves this form. So all of this that we're learning here is actually deeply connected. Let's see some examples and non-examples. The first example I have here is the span of the set V1, V2, and V3 as a subset of Rn. Alright, we have to check three things here. The first thing we gotta check is, let's call this, first off, let me back up a step. Let's say S is the span of V1, V2, and V3. So the first question is 0 an element of S? Well, yeah, it is, because the definition of span is it's all possible linear combinations of those vectors. And 0v1 plus 0v2 plus 0v3 indeed equals 0. And so therefore, we're good. 2, we need to be closed under sums. Well, again, I'll be lazy. Let's look at this. If I set this coefficient to 1 and this coefficient to 1, so that I have v1 plus v2, S is by definition then the sum of... Oh, goodness. I've confused myself in my wording. What I'm trying to say here is v1 plus v2 is a linear combination, and therefore it's in the span, and therefore it's in S. So yes, this is in S. And in fact, if I take any two vectors, I can express them as a linear combination of those. So yes, we're good. All right, number 3, scalar multiples. All right, if I take any vector, I get that. And that is going to be expressible as a linear combination. All right, any line or plane through the origin, that's the key here, in R2. All right, is a zero vector in there? Well, yeah, it is. All right, now if I add up two lines, so y equals m1x and y equals m2x, that's still going to pass through the origin, isn't it? So we're all good there. And if I do a scalar multiple, all I'm doing is just adjusting my slope, and I still pass through the origin. So yes, that is another subspace. And you can do the same argument for a plane. All right, the set of all vectors of the form an even number, comma 0. And that even number happens to be 2z there. All right, so what I have is, I'll write it like this, an even comma 0. Well, is the 0 vector in here? Well, yeah, because 0 is even. So 0, check. How about the sum? All right. Okay, sorry about that. Someone just came to my office and asked me a question, and I've completely lost track of where I was. So what we were doing was saying that 0's in there. I remember doing that because it's on the screen here. What I don't remember doing is the sum part. So let's go to there. So what I have here is an even comma 0 plus another even let's call it even bar, comma 0. Well, hopefully you all remember that if you add up two evens, you get another even number. So let's call it double bar. So yes, it is closed under sums. The next thing we need to worry about is it closed under scalar multiplication? Now, this is where it gets a little tricky, because what we need to do here is take a constant. Well, that constant has to be a real number. So what we see here is if I take a real number, 2 alpha times some k, because 2k is the even number I'm thinking of here, comma 0, is that necessarily 2 times an integer? Well, no, it's not. And so therefore, this does not form a subspace. All right, the sum of all vectors where you have an odd number, comma 0. Well, I think given the last example, you should all be able to see that this will not form a subspace either, for the very same reason that the other one failed. But what's interesting is this one actually fails the sum property, because if you think about it, an odd plus an odd is equal to an even. Not only that, does this thing even have the 0 vector? No, it doesn't. And so this fails on 2 accounts. The 0 set. Now this one's super cool. So definitely the 0 set is a subspace, or an element of this rather. Now the sum, well, if I add up any two 0 vectors, I definitely get another 0 vector. All right, and scalar multiples. If I do a constant times 0, well, I keep 0. So yes, this is a subspace. All right, now what we're going to do here is think about subspaces in terms of matrices. So if I give you a matrix A, and it's given by its columns, the column space is simply the span of the columns. We'll denote that by col of A. Some books will use this script notation, but I won't. All right, now, if we think about this, if A is m by n, so we have m rows and n columns, then the column space of A is a subspace of Rm. All right, this is pretty easy to see right here. Why is that? Well, actually, I'm jumping the gun here. It's a subset. Each one of these is a column, so that's, say, A1 there. A1 is an element of Rm. So that means the column space is a subset. Now, it's a subspace for the same argument, that, the 0 vector's in there, because this is the span. In fact, if you think about it, the span of any collection of vectors is going to be a subspace. All right, and so I'm going to ask the question of you, is that particular vector right here in the column space of this? Well, what's the column space? It's the span of the columns of the matrix. So what I'm really asking here is 1, negative 1, 2 an element? I'm going to call this A1, A2, and A3 to make my life easy. An element of the span of A1, A2, A3. Well, to ask if this is in the span is actually to ask, equivalently, does there exist alpha 1, alpha 2, and alpha 3 real numbers such that alpha 1, A1, plus alpha 2, A2, plus alpha 3, A3 equals 1, negative 1, 2. Well, going back, this is a vector equation. Every vector equation can be written in augmented form. And so us asking 1, is this in the span? 2, are there weights that satisfy this? And 3 is us equivalently asking, does the vector equation, the matrix equation, if I call this capital A times alpha 1, alpha 2, alpha 3 equal 1, negative 1, 2, have a solution? Well, we know how to do that. We simply write A, which is 1, 1, negative 1, and 1, 2, 2, and 1, 1, 1. We augment that with 1, negative 1, 2. And we simply ask, is this system consistent? All right, well, I'm going to pop this into my handy-dandy calculator. Oops, that's not what I want to do. I want to do RREF. My handy-dandy calculator tells me that the reduced to echelon form here is exactly this. And we see immediately then that alpha 1 is negative 3 halves, alpha 2 is negative 2, and alpha 3 is 9 halves. So, to answer the question, is that vector in the column space? We say yes. It is in column space of A. Not so bad. The next one, the null space. So the null space of a matrix is a set of all solutions to the homogeneous equation. All right. So what we have here is AX equals 0. Okay, if you think about null of A, that's going to be a subset of Rn. Now, why is that the case? Well, if A in X, that equals 0, if A is m by n, if we're a solution to this equation, then X must be n by 1. And so that makes it a vector in Rn. So that's why that's the case. Now, the subspace part is actually interesting. This requires a little bit of work. Let's prove it. So the first criterion for being a subspace is you have to have the 0 vector. Well, we know that the homogeneous equation is always consistent because A times 0 is 0. So yes, 0 is an element of the null space of A. So that's good. 2, we now need to check that if I have 2 vectors in the null space of A, then their sum is also in the null space of A. Well, look at this. If I do A of x plus y, by properties of matrix multiplication, this is AX plus AY. But recall that x and y are the null space. Well, that forces AX then to be 0 and AY to be 0. And of course, 0 plus 0 is 0. So, yes, x plus y is in the null space. And finally, 3, if I take an arbitrary vector in the null space, and I take any real number, I need to test that alpha x is also in the null space. Okay, well, let's consider A of alpha x. Again, by properties of matrix multiplication and scalars, I can pull that out front, like so. By assumption, x is in the null space, so this is alpha times 0, which of course is 0. So, not so bad. All right, let's look at this example. Suppose I have AU and AV both equal 0. Now, before I move on, that immediately tells me that U and V are elements of the null space of A, right? Because they are both solutions to the homogeneous equation. And I'm just happening to give you what those explicit vectors are. Now, what I need to do here is determine A of U plus V. And then I ask, is that an element of the null space of A? Okay, well, A of U plus V, or A times U plus V, however you want to view it, that's nothing more than AU plus AV. Without any calculation at all, we know immediately that this must be 0. Next up, is this particular vector in the null space? And I should really be saying it's transpose here. Well, the easiest way to test that is to perform A times negative 10 for negative 13, right? But the problem is, we do not know A. Well, it turns out we actually don't need to know it, because what we have here, 2 vectors. All right, So think about this. I know that the null space of A is a subspace. So that means that it is closed under scalar multiples and sums. So that means if I can find some alpha and beta that are real numbers, such that alpha times u plus beta times v equals -10 for -13, then I can definitely say that this particular vector is in the null space. Now, we have to be very, very careful here. So let me back up a step. Let's call this thing B for the sake of argument. So if this has a solution, then B is in the null space of A. That we can definitely say. Because if I then do A of this, I think y'all see that you'll get 0, right? Because the scalar comes out. All right, now the thing is, if this thing does not have a solution, so if there's no alpha and beta such that this linear combination will give me B, that does not mean that B is not in the null space of A. You got to think about why that's the case. So if this does not have a solution, we cannot say B is not in the null space of A. Because how are we to know that these are the only two vectors that really, I guess you could say, typify the null space? Perhaps there's more vectors in there that do more. I'm having to be purposely very ambiguous in my language because we haven't learned what a basis is yet. But what I'm trying to say here is we do not know that those form a basis for the null space or not. It's quite possible that they don't. So without further ado, let's actually determine if this is a linear combination of u and v. So the question is B an element of the span of u and v? Well, that's the same thing as forming an augmented matrix with u, v, and b. Right? Can I jump that far of a jump right now with y'all? I hope so. All right, so let's make this augmented matrix up. So u is 0, 1, -2, v is -2, 0, 3, and b is -10, 4, -13. And what I need to do here is figure out if this is consistent or not, or if there's, well, just need to figure out if it's consistent. So here we go. Let me pop it into my handy calculator. Okay, what I ended up with is very interesting. I get 1, 0, 0, 0, 1, 0. Excuse me. Sorry with that coughing. We just started school a couple days ago, and I think I've got a cold. I think you can probably tell by today's lecture. It's been rough. Anyways, this right here tells us since we have a pivot in the right-hand column, it's bad news bears. So we have no solution. And therefore, go back up here, ask him if it's the null space of A. Well, we can't answer that, can we? We don't know. We cannot say if B is in the null space of A. We need further information. All right, we finally get to the definition I've been waiting for. I keep on saying this basis word, and y'all have any idea what I mean. Now we'll know. And I even up here, right? Finally a definition for basis. So a set B, subset of Rn, is a basis for some subspace if that particular set B here is both linearly independent and it spans, oh, that's supposed to be a S. So the criteria are linearly independent and span. And if I want to paraphrase this, we are saying here that we can efficiently get everywhere we need to go. So the efficiently is me saying it's linearly independent. I do not have any vectors that I don't need, right? If I had a dependence relation, that would mean that one of the vectors is a linear combination of the others. Well, that would mean I had a vector I didn't need. So that's where efficiently comes from. And get everywhere I need to, getting everywhere is me saying I span, because the spans all linear combinations. So every linear combination I need to be able to make, I can make it. So a basis is nothing more than a very efficient way of getting places. You'll remember I called something a canonical basis, and that was E1, E2, up to En with the hats, as all viewed inside of Rn. Well, if you think about it, with these n vectors, they're definitely linearly independent, because if I form a matrix out of them, I get the identity matrix, right? In the whole spanning business, well, every vector in Rn is a linear combination of these, where I just take, so x1 down to xn is the vector. x1 through xn are the weights on the e's here, so I span. And so that's why this basis is so nice. It's a very clear choice of a basis. All right, let me actually back up a slide. All right, now what I want to do here is give a basis for the null space and column space of A, if that is my particular matrix. All right. To start off, what we'll do is actually put this in reduced to echelon form. So 3, 2, 3, -6, 4, -4, -6, 9, 7, 6, 0, 2, -6. The reason I'm jumping straight to the RREF will hopefully be made clear once I get there and do my explanation. All right, so what we have here is this particular matrix. What I want to do immediately is identify the pivots. There are only 2 of them. Now what you should think about is these 2 pivot columns correspond in this manner, as we see here. And so this pivot column, corresponding to this column of the matrix A, allows me to say that the column space of A is the span of column 1, which is 3, 2, 3, and column 2, or 3 rather, which is 9, 7, 6. You might be confused as to why I use the columns from A and not the reduced or echelon form of A. I think the easiest way of seeing this is as follows. The column space of A is the span of these columns. Now look over here at this matrix. If I'm taking this span, that means I'm taking all linear combinations of the columns of this matrix. Well, if you'll notice, the last row here, the Z row if you want to call it that, actually has numbers in it, 3s and -6s and such, just like over here. Now if I look over here, those are all zeros. There's no way for me to take a linear combination of the first and third columns here to get a number in that third entry. And so from that, I think you should be able to see that it's impossible for us to actually use the columns that reduce our echelon form. All right, now to get the null space, we actually can just use this matrix we have right here, because what happens is, if I form the augmented matrix A0, that's me solving the homogeneous system, that's the same thing as me, after reducing this matrix to Lord knows what I get here, with a 0. Now think about it. If I'm doing row operations on A, like I did over here, and I put a 0 in the right-hand column, that 0 column's never going to change. And so all I've really got to do, I'm just going to be lazy, is take the reduced or echelon form and augment it with 0, and that will be where I can make my inferences. So let me do that. I have 1, -2, 0, -6, 0, 0, 0, 1, 2, 0, and then a nice big 0 row. So that's the homogeneous system there I'm looking at. Well, I convert this back into a system of equations. So this is x1 equals 2x2 plus 6x4. x2 equals x2. You notice there's no pivot there in the x2 column. x3, well, that's -2 x4, and x4 equals x4. Now when I convert this to a vector, I have the vector x is equal to 2, 1, 0, 0 with an x2 plus a 6, 0, -2, 1 on the x4 there. All right. These two vectors form the basis for our null space, because any vector x that's going to be a solution to this system here is a linear combination of these two vectors. So a basis for the null space of A is then the set 2, 1, 0, 0, 6, 0, -2, 1. All right. Now, how can we get a basis for the column space of a matrix? Well, this is what I was talking about from the last example. A basis for the column space of A is formed by the pivot columns of A. So note the pivot column is A for, that's supposed to be a form, the basis, and not the pivot columns of any reduced form of A. All right, and that's the theorem here. The pivot columns of A form a basis for the column space of A. And that's the end of this section.